tailored solutions for your most complex challenges, comprehensive results that help communities, economies, and natural places thrive. We're the team whose engineering and environmental expertise delivers these outcomes. Around the globe, our engineers, scientists, and technical specialists focus on solving our clients' problems as if they were our own. With BAR's resourcefulness and dedication, you'll find solutions in engineering and design, environmental investigation and remediation, permitting and compliance, sustainability and resiliency, and water management. All our work begins with listening, because your problem deserves a tailored solution from consultants who share your passion and integrity. Because your evolving needs require an agile partner who can dive in and assist at any point along the way. We're here at every step to deliver an exceptional experience, sustainable solutions, peace of mind. Together with BAR, you'll find the best answers to your biggest challenges. At BAR, we're here to help you with your mining project from concept to closure. If you can mine it, smelt it, move it, or store it, we'll be there. If you can design it, build it, power it, or repurpose it, we'll be there. We help with environmental services, mine geology, mineral processing, material handling, facility and site design, plus tailings management. We'll be there for water resources management, field performance monitoring, mine closure, remediation, reclamation, and more. We'll meet you at any step of the way. We're an employee-owned company with world-class expertise and a nimble, flexible approach that puts you first. Our commodities experience extends from nonmetals and industrial minerals such as potash, coal, and sands, to metals such as iron ore and copper. From precious metals such as gold and silver to rare earths. You need consultants you can count on. If you can dig it, process it, or store it, BAR can accomplish it.
All right, good morning, everybody. Welcome to Best Practices for Slope Monitoring Safety in the Aggregate Industry webinar. I'm Kyle Fitzinger, a mining engineer at BAR, and I'll be your host for today's webinar. Thank you for joining us. Today's webinar will provide valuable insights to help you proactively identify, monitor, and mitigate geological risks to your operations. BAR has assisted national and international mining and mineral processing clients with complex, large-scale projects for more than 60 years. We offer assistance with everything along the mining development lifecycle. By integrating engineering and environmental expertise, we can provide a streamlined approach to your project, one that improves efficiency, communication, and understanding of both the small details and the big picture. Before we begin today's webinar, here's some logistics. First, if you're having issues with the chat features or with the presentation in general, please send an email to our administrative support, Lisa Ungar. Her email is listed below. Also today, we will be using two items to submit questions. The first will be the Q&A feature on your presentation that is located on the upper toolbar, Q&A with the chat bubbles. The second, you can see the white link below. Here. Please use this feature to submit questions as we progress. These questions will be addressed and answered at the end of the presentation. First, we'll hear from Russ Sheets, a senior geotechnical engineer with BAR. He has 17 years of experience using geological information to understand site conditions and provide recommendations for geotechnical projects. His experience includes site hazard inspections, implementing monitoring systems to understand soil and rock behavior, and developing trigger action response plans for operations. Russ has a bachelor's degree in geological engineering from Montana Tech and a master's degree also in geological engineering from the University of Wisconsin. Russ is registered professional in 11 states. Then we'll hear from Michael Haggerty, a Vice President and Senior Geotechnical Engineer with Barr Engineering in Minneapolis, Minnesota. His work involves tailing basin assessment and design, mine pit wall stability, ground control assessment for mines, tunnel rehabilitation, and underground structures. Michael has undergraduate degrees, undergraduate degrees in geology and geoengineering, and a master's degree in civil engineering from the University of Minnesota. He is a registered PE in 10 states. Now, before we learn about our topic areas, we'll have a brief safety share. October is National Pedestrian Safety Month. Typically, we think of pedestrian safety involving interactions between vehicles and people at home. The weather is changing. People are out at different hours compared. Sunlight can make it difficult to see. And as the weather cools, people may tend to wear darker clothing when they go on their evening walks. So please watch out for them at home. At work, at our operations as well, shift change may occur at dusk or dawn now with harder to see conditions. Also, as the weather cools, we may get freeze-thaw conditions on our high walls. So today, not only think about the safety of your folks on the ground around vehicles, but around high walls as well as we inspect them. Now we'll turn it over to Russ. Russ?
All right, thanks. Thanks, Kyle. You get everything switched over here. As he said, yeah, we're gonna be focusing on what you need at your operation. So we're going to be looking for your day-to-day staff, your supervisors, your leadmen. So we're not going to necessarily dive too far into the technical aspects of this geotechnical discussions. We really want to make sure we line you up and just communicate some tools that you guys all can use, and hopefully are readily available to you at your operation. We're just going to talk a little bit about the why. Why are we here? Why is it important? Why do we need to be concerned about geohazards with regards to just keeping our folks safe? A little bit on the fundamentals, what sort of slope stability issues you may encounter depending on if you're, sand to gravel or rock quarry. Then we'll transition over. Mike will take over, talk a bit about ground control plans and maybe what are some of the regulatory aspects of what we have. And we'll share some examples of monitoring methods and then dive in a little bit at the end of, okay, you've done all this stuff. What do you need to do to implement it and use it at your operation? So we'll start a little bit with some of the why. So when it comes to ground control mining industry, regardless of your scale, when you're looking at the geohazards of keeping folks safe, is we consider that it's not a matter of if, but when a slope failure, slope movement can occur. And, we all may be thinking, well, yeah, large scale movements, they're the ones at risk. But if we're just talking everything in general, that could be a large scale movement just down to, rockfall, gravel, local sloughing. We see some of this stuff day to day. There's going to be some inherently always some movement as you're exposing ground conditions, opening it up. Usually our bench faces are a little steeper than what that natural condition was. We're going to see something coming off, raveling off, and it's just understanding, well, what's the type scale risk we could have off of that. Now, the fortunate thing is here, obviously, we can all keep going. We can keep our folks safe. We can continue to mine as long as we have the practices, we have the controls in place. We know what to look for, and importantly, we know when we do see those changes in conditions, we know how to respond, how to react. Is that fixing maybe fixing the instability with some earthwork, or is that, we're just going to berm off, barricade the area, we'll step back a bit, let it do its thing, and then move on from there for, how do we mitigate it, making sure we keep folks safe. And so the benefit here is all slope movement that occurs is there's going to be signs, whether it's that crack, the sloughing, the raveling. Now, the one catch that we all can sit here and ask is what's the time period? Depending on your, ground conditions is, maybe that ranges from hours to years, slow moving, large scale. But in all cases, we can keep going. We can keep folks safe as long as we know what we're looking for. We know how to respond. And like I said, we have that plan in place. For when those conditions occur. Now, just a little bit of an example here of not if but when case. This is a larger scale coal operation, but as we can see here, we've had kind of a significant movement. So it's not just the hazards that slope movement can cause to your personnel, your equipment, your operation, but then it's the impact on the business side of the mining. So, you've developed a plan, you're going to have, a specified working room working with, you have a larger scale slope movement that pushes in, reduces your pit width, or reduces the working area. And in this case, it essentially creates a pinch point because, like you say here, it's a narrow pit. So you've got folks, their only way in or out is kind of working laterally. But you see, large scale movement here, pit moved out at least 100 feet, pinching that pit floor. In the case here, then you get into the regulatory aspect of, even if you were aware of it in advance, if it is a significant movement, you can maybe get MSHA involved. And in this case, they issued a K order on the operation, which, although no one was hurt, the order then specifies kind of their control of the process of then what you need to go through and what they need to approve before you can safely get back to operation. Now, as I said, the biggest thing with ground control issues is just what type of rock or soil are you dealing with. And this can bring in where kind of a case-by-case basis. There's a lot of geographies that I know many of you in attendance may be working in. And it's knowing and understanding that, okay, maybe some of the issues, some of the risks, some of the methods that maybe at some point in your career you saw applied at one location, one operation, maybe they don't entirely fit the next one. There may be that something that'll work better. And that's hopefully what we get into is just the methods that you can try and plan ahead prior to a ground event occurring, trying to keep it from being an unexpected impact on your operations. So now we're going to jump into a little bit of the fundamentals. And like I said, we're not going to dive too much into technical, but we just want to set the framework for, well, why are we here? Why are we talking about this? Why is this important to you? So when it comes to designing any size pit, general concept is we know there's more minimal exposure compared to, say, a large earthen or concrete dam, a skyscraper. You get into some other industries, aviation, where failure because of that exposure to the public is just not acceptable. The public expects everything to be safe, stay safe, no issues. And an aspect of that is your general person doesn't know what to look for, say, in a dam inspection. Whereas comparatively, mining industry, we've got a lot of pits. Conditions are constantly changing. We're either expanding, laying back a pit, or we've mined out an area, closed it, reclaimed it, and we're on to someplace else. Maybe depending on the size scale of your operations, maybe it's a few months to every couple of years. And you have the equipment there to address issues when they occur. And the staff, that's part of all our MSHA training is ground control. What do we look for? Make sure we get it reported. So although the risk and the probability of almost certainty that you're going to have some size aspect of failure, you have a lot of the controls in place to make sure it's not going to have an adverse impact. And this is important key. We've got our pie diagram off, and just so we all know and understand that it's not just necessarily one aspect that creates the risk. You have different types of risk, like I said, based on whether you're sand or gravel, whether you're a rock quarry, and even in that rock quarry, do you have different geologies? Are there different layers, bedding, fractures, joints, some of them coming up, groundwater, do you have the ability to collect data through drilling or just face mapping? And then, what's not shown here is just the operation. Well, how do you drill? Do you need to drill and blast? How do you drill and blast? What kind, size, type of equipment are you using to excavate? Just any number of these factors that can impact what we're doing. So talk about basic types of failures, but we're going to frame it here. Some of these examples we looked at and pulled from MSHA. You said a lot of safety, a lot of risk, a lot of issues. Not that ground issues don't account for a lot of accidents, fatalities we see on the MSHA side, but they do occur. Rock falls. Image right here on the left, you got a chunk fragment block of rock that becomes either undercut, loose, fractured, just able to fall out. And as you can see, we've got a blast hole rig here that ended in a fatality because the blocks of rock landed on the cab. Example on the right, more of your soil, granular based material, just an overall slide slump, waste dump fill material here. A shear failure that can cause that to slide out as it locally tries to develop its own angular repose if it had been constructed too steep. Toppling failures, can be a little bit like rockfall, depending on how your joints, your fractures are maybe dipping into your slope, into your high wall, and then just due to gravity, your centroid there, you get the rocks and fragments just kind of tumbling out, falling out of the face. And in this case here, if you can see it in the rubble, they do have a piece of equipment here that was impacted. And then last one, we'll just kind of show here as an example, is just kind of that transitional large block, kind of like a slide, but example here, we've got some cracks, they actually show heave, where the base of the floor of the pit is starting to try and push up, heave up. We've got a massive block that's sitting on a weak zone, weak layer it's able to translate and slide into the pit, into your area of workings. So with that, I'm going to transition. I'm going to hand it over to Mike, and he's now going to take this the next step through that, your ground control plans, as well as some of the regulatory aspects of this.
Great, thanks, Russ. As Russ mentioned, I'm Mike Haggerty, and I'm going to be talking a little bit about ground control plans and also the first half of monitoring methods that might be applicable to your site. So Russ talked a little bit about the why, what's important with regards to ground control plan, why, slope stability at a quarry operation, at an operation, two big motivators that fall into that. Certainly the number one item is safety, making sure miner safety is prominent in any of the planning of the site. The second one is a good understanding of your ground conditions plays into avoidance of unexpected downtime in operations. So you can adjust depending upon what the operations are to what you're going to see on the site. And those things, as Russ mentioned, oftentimes change as the mine operation has progressed through its ore body or pit. And so good to be aware of it so that you can maintain safety, but also avoid those unplanned shutdowns. And when you look at what MSHA requires, certainly they're looking at it from the miner safety standpoint and some of the CFR language around what's required there. It's certainly open. The bottom line is really you should have a plan in place such that failure doesn't occur or minimize any certainly exposure to safety on regards to that. But when you look at the actual language, so each operator shall establish and follow a ground control plan for the safe control of high walls, pits, and spoil banks to be developed and be consistent with prudent engineering design and will ensure safe working conditions. Mining method employed by the operator shall be selected to ensure high wall and spoil bank stability. Interacted with a lot of MSHA folks through the years, and I would say, you bring some standards of care from a slope stability standpoint into your mine operation. When they talk about prudent engineering design, you want to make sure you're taking that into consideration. If it fails, something was missed, whether it's certainly not intentional, but something was missed. And so having a good understanding of what to look for before that failure happens is very helpful. So really the focus then is with the operations that you have on site, how are you operating to maintain that high wall stability? Do you need benching? What is the width and height of those benches? Do you need to scale the walls? All of that falls back onto what sort of an operation are you looking at. So there's not required, ground control plans are not specifically required for quarries and sand and gravel pits. However, if ground control citation is written or an accident occurs, MSHA can request to see your plan, or they can require a written plan or a written plan that has to be developed to abate a citation and lift a K order in an accident area. And so it's good to, no matter what sort of operation you are, to be thinking about that. What is best practice? Do you understand the risks that might be at your site? And then what are the approaches to mitigating that risk? Oftentimes that can come down to monitoring, which we'll talk about in a little bit. So one of the basic things is just good education of site staff, and all sites are required to train staff in ground control hazards. So what to look for, what risks need to be mitigated. So your inspection should cover those same topics, your site specific inspections. And as discussed earlier, that inspection must be documented. So you want to provide record of conditions over time, both good and bad. And then when you identify something that is of concern, how and what are you doing to mitigate that? Those are the key things you want to make sure you have in your documentation. And it's always good to think about this, particularly at a quarry mine site in terms of risk. And as we have here, risk, really that probability of failure versus consequence. You know, if you're a giant open pit, say copper or gold operation with, you know, a main haul road that's coming down, that's going to warrant a certain level or a higher level of monitoring to get early warning on something negative happening to that pit. If you are a smaller, let's say a limestone operation, and you've got a pit that you don't work in that often, you know, visual observation might be appropriate because there's not a lot of workers back there. You might get some toppling, but it's not something that's of a dramatic risk to either the miners or the operation. So you have to weigh what is the risk to any particular part of your site, and then you can start to develop a basis for why and what sort of monitoring you may want to employ at that particular spot. So with that in mind, there's a whole host of monitoring methods. I'm going to talk through what I'll say is kind of probably the more standardized ones in terms of like visual observation, things to be looking for, qualitative type of awareness, and then I'll toss it back to Russ, and Russ is going to walk through some of the quantitative or more quantitative types of measurements that can be done on operations. So talking about, you know, slope deformation monitoring, as was mentioned earlier, a lot of times there are warning signs that are happening before a significant failure can occur. And it's good to be mindful of what those keys are, what those signs are, so you can take action. And so you really want to transition from a qualitative data using, you know, photos and videos to document conditions and try to quantify site conditions and measure the site features. Those are the things that kind of run the span of what you can do at a site. I'll talk a little bit about, you know, visual photographs, drone, LiDARs, and then, as I mentioned, Russ will talk more about the monitoring pieces. But there's a whole host of things that can put you in a good position to keep monitoring on your site. The basic of these is regular routine visual inspection of the slopes. A lot of times this will be, you know, at the beginning of each shift, the pit foreman may be looking at things and documenting them. So that's your eyes and ears, someone who sees that ground every single day and has a pretty good sense on if conditions are changing unexpectedly. That's a really good line of defense and something everyone should be educated in. But then there's also another whole host of items that you can use for slope monitoring, everything from, you know, surveying of prisms, GPS, aerial drone, LiDAR, INSAR, and then you get into some of the specific instrumentation pieces that can be used, like extensometers, inclinometers, shape array, those sorts of things. But it all really starts with the routine inspection or the visual inspection. When you look at the whole host of instruments that can be done, there's no one item that does it all. And that's important to keep in mind, because you will hear a lot about, you know, various types of instrumentation. They're all good in the right setting, but they may not be the right one for your site. And so it is important to understand the host of what is out there and the impact and the costs and the benefits of these things, and then use that to kind of weigh in on what fits best for your site. This is a kind of a qualitative layout of that range, and going through this just to give you an example of some of these specifics, everything from, say, a GPS survey, where you may be looking at, is there movement at the top of a high wall, taking points on a regular basis with a surveyor and looking for movement. You know, that's something that's relatively straightforward, but you may have limits on access to get to a spot safely, but you have a fairly high degree of accuracy with the repeatability associated with that. Next, you move down, you could look at an automated manual prism survey. Again, you're able to repeat, high repeatability, high accuracy. You need a prism installed to achieve that accuracy, so there may be some limitations on access to a particular area of concern if it's on a high wall, let's say. Drones or UAV, that's something that a lot of mine sites have certainly employed. I'd say over the last 10 years, it's fairly common. This gives you the ability to get that aerial visual look at the site, and maybe see things you weren't necessarily able to see from the pit floor. It also allows you the opportunity to get sometimes LiDAR scans or something like that. So it just augments your ability to more efficiently get information. You've got to be able to process it and have the time and the staff and the resources to go through it to understand what you're seeing. But it is something that adds some efficiency. You can look at an automated manual laser scanner. This is where you just set up a single unit, and it will kind of automatically on a regular rotation go through and scan different areas. Again, you start to get away from access issues, and you get a high degree of repeatability, but a lot of data that has to be gone through. And so now kind of ramping up, this is something that maybe is more pertinent for a high risk area, something that's really critical to the site. And you'll see some of those fixed scanners that are on areas where there's high components or highly trafficked roads within the site, and it kind of transitions into this next one, which is really the radar scanner. A lot of times you will see these sorts of units. It's a single source unit that's on a large operation scanning a critical high wall on some of the big mines out west. Again, the dollars range on this and the amount of effort to process that data ranges as well, but there's a whole host of things here. And finally, the last one that we had on this one is INSAR. INSAR is looking at satellite imagery and processing that so that we can get an idea on if there has been movement. So it's a little bit of a lagging measure. It's relatively cheap or inexpensive to apply. And so in areas where there's, maybe remote and you don't have the ability to put in instruments or staff loads, excuse me, it provides a way to look backwards at what's going on. So going back to kind of the visual take on all this, regular visual inspections of slopes, photographs, and imagery, these are things that can really be done on a regular basis to document working conditions. You're looking for geology, hydrology, excuse me. Some of the methods for observing and documenting pit slopes include camera or phones, video from drone. Any of those things are relatively easy to implement and pretty common to have. A few examples that we've got here. So this, excuse me. This is a massive limestone wall, high wall at a site. You can see bedding planes and fractures. You might get raveling from something here. You could have toppling or rock blocks falling. And so those are some things that you'd be looking for. Voids or karst, you can see the bedding planes. Those are the sorts of things that on a visual inspection day to day, you can see if there's been some changes that pose risk to the site. Now, by comparison, you look at, this is a picture of a high wall from northern Minnesota. It's different than the limestone because there's a lot more fracturing, there's a lot more structure. There's some weathering at the top. And so looking at the top for toppling rocks, things that are coming down, the higher degree of the fracture of the rock is something that would raise a concern or something that you need to pay particular attention to. This is another site from Wisconsin where it's a banded rhyolite. It's a little more challenging to tell here, but the dark material seems to be a little more fractured than the tan material. So joint sets are present, and one of the important things to notice is the dip direction of these fractures. So changing geology is something to be aware of as you continue to look and assess your pit and see what those changes are. Now, the next few pictures are from a sand plant site or a sand pit, and you can see there's geologic variation in this picture. You can see the change in coloration as you move down the pit wall from the top to the bottom. And this could be representation of a different portion of that material, something that's got more binder, cement holding the grains together. It could be something with moisture, but it's something to take note of. You can see a layer of some more cobbly material at the mid bench, and then towards the toe, you can start to see some cross bedding. All those things are good observations to assess to see if the material is changing as you're exposing that wall. And this is that same pit, but if you look, if we're looking down the pit slope itself, now you can start to see that there's a relatively steeper angle at the top, and then it fans out or gets to a shallower slope. This again aligns with that darker material that we had in the beginning. And that, again, it could be either over steepened or it could be an area of higher risk that with time might start to unravel on you. And other than that, it's fairly uniform all the way down here. But this sort of steeper slope at the top, again, is something you'd want to pick up on your visual inspection, because that can change with time and it can be a warning sign. So it's good practice to document face conditions like this. Is the material creating a good muck pile to dig from, or are you observing a more near vertical conditions and potentially undercutting that with operations? This is that same pit, but moving back in scale a little bit higher with a drone image. And now you can start to look from that aerial view and see what the benefits are of this perspective relative to the pit floor. You can see some cracking, some tension cracking up at the top here. On this particular case, that aligns with some of that steeper material. And so those are signs that you might have a small localized failure there. In a harder rock type of operation, you could see some backbreak, potential impacts from blasting that may be loosened areas, and help you identify areas that need to be scaled. And then same thing here, it shows a few other things. So first, again, you get a better perspective on where there's fractures developing at the top of your high wall. And that's something that could pose a particular risk. And here you can see the changes in the geology really well, the steep top part, the fanning out, some of the different materials. But the third item to note, and is important to think about when you're laying out your visual observations, is the shadowing. So this shadowing, in this photo, it's hiding some of the features. And so one thing that's important to think about in your planning is, get a look at different times of the day. Make sure there's not an area that's completely hidden. But on top of that, it's good to be consistent from day to day as well, so that you can see things, from the same angles, and make sure that there's no changes that are there, but just going unnoticed because of the angle or the time of day that you're doing your inspection. Ideally, you want to have well-lit conditions, makes it easier to compare to the past days. And this just shows you that giant shaded area out here. Hard to see anything on that wall, so you'd want to catch that at another time. Here, there's some shadowing that, again, a different time of day might expose what that looks like. And same thing here. So just some general rules of thumb to be thinking about. And then if you go back even further, one step, you can see that wall in the background here. Again, with a drone, kind of get an overview of the site. There's a few other things that you can think of. So it gives you a better perspective of kind of the rolling topography and where surface water may be concentrated to, if that's coming to the top of a high wall, or causing issues with water spillover on your high wall or anywhere on your site. And then you can also pick out bench conditions and just in general notice drainage patterns. You can see along that pit, where's the high ground, where's the low ground. Again, in a storm situation, you might get a concentration of water that, let's say, if you have a loose particular sand, might be more prone to raveling out during those rainstorm events. Now, with that, I'll toss it back to Russ here in a second, but the big thing is data management, and your consistency is key on those visual type inspections: location, angle, lighting, camera, all things you want to think about and consider when you're laying out your visual observations. Russ?
All right, thanks, Mike. So now Mike has taken us through kind of the conceptually what we can do is particularly the visual inspection, which is the ground base of anything we're doing, is just getting eyes out, looking at your operation, looking at your site, looking at your geology conditions, and just tracking what's going on. I guess I'll point out, also kind of talked about some of the toys, the instrumentation, the equipment to try and quantify this, and they all have their benefits, drawbacks, costs. Nothing's entirely perfect. You really need to look at what you need, what you need for your situation. But also want to point out too is we're not now saying that, oh, as soon as you get off this webinar, you need to call up your vendors and say, you know, I need a robot, I need a radar, you know, how do I get INSAR? You don't necessarily need to do all that. It's just starting with understanding, doing what you can, and then we really just want to make you aware of what's out there, you know, what tools are out there. So, you know, as you're starting to see those changing conditions, or maybe conversely, your operations, you know, your quarries, sand gravel operation is in a little bit more urban or closer environment, you're getting close to that property boundary, and you know, maybe the neighbor there, maybe part of it isn't so much you've got a hazard risk to your own operation, but it's just ensuring, verifying that, you know, you're not impacting, you know, whatever happens to be next year around you. So anyway, we're going to go through some some pseudo case study examples to show you what some of these are, what some of the data looks like, and like I said, just make you all aware of what are some of the tools out there. So if we take it from just the visual inspections, you know, just kind of very rudimentary, what can we do? How can we quantify movement? The image on the left is, you can't really see it, but we're going to talk pin sets. So whether it's a stake, a nail, rebar, you know, something you pound, install in the ground. We've got some, you know, flagging material a bit on either side, and, you know, obviously there's a crack. There's signs of movement here, but it's just placing two fixed points in the ground. In this case, tape measure of some sort, be able to measure across. You know, maybe you got multiple pins, so you can, you know, try and triangulate and try and gauge, understand, well, which direction things may be moving or accelerating greater than others. But just a basic, you know, let's see what's moving. You know, let's put a distance to it. I mean, we'll simplify this even more. It's you know, what matches a visual. Example I have years ago, I was called out to go look at a pit and, you know, meet the foreman up there, but I beat him to the site, and I find a rolled up newspaper magazine with some paint or marker on it shoved down in the crack. And I'm looking at it, foreman comes up and he says, well, this is what I had with me. I figured that if this happens to be rapidly opening up, either, you know, that newspaper will unroll or it'll drop, and the marker I had on it will, you know, be a hard set visual, other than just say comparing photos that something's changed. And just kind of look at him and be like, well, yeah, you're right, that makes sense. It's really simple, really rudimentary, but, you know, it's kind of some of the, you know, that wouldn't work long term, but it's just kind of that basic initial, you know, how do we mark the ground? Image to the right here, you see the orange painted lines. Now, again, depending on geology or weather conditions, you may need to be out there frequent enough just to refresh some of these, but, you know, paint some orange lines on the cracks, paint them kind of perpendicular to the cracks. So obviously, if things start moving, pulling apart, you're going to start seeing a gap in that line of orange paint you painted. So yeah, you're taking photos, but depending on how you look at it, you go back to the shading, the shadowing Mike was talking about. Depending on how the lights hits it, you may be like, well, did that move, or is it just, you know, we got different shadowing this time? Another example monitoring here is an extensometer. This one, yeah, we'll say a little fancier. It's a commercial available one that I've used many times in the past. Strobe light attached to it. Basically kind of like the pin set, you got your fixed point. So this one, there's a stake on the opposite side. So if this is pulling away, it pulls on the wire, pulls the counterweight, and then there's basically a gauge, a measuring, you know, say meter stick or something attached to the side of it, and you can measure, okay, change over time, you know, how much has this moved, how much has it displaced. Now, this one, a bit more manual. They make automated telemetry ones. Also seen it as simple as, you know, fashioned homemade ones at mine sites with some angle iron, steel pipe tubing, where they kind of build the same tripod and put a counterweight attached to a wire in one of the angles. So as things pull away, the counterweight pulls up and you can measure that. So, you know, kind of like I said, is, you know, there definitely are the commercial tools available out there, but, you know, there's also ways to at least initially start with, well, what do you have at hand? What can you use? Now we talked a little bit about survey prisms and use survey total stations, whether it's manual, you know, you have a surveyor technician, someone who can go out and shoot these on a regular basis, to the opposite extreme where, you know, there are software programs that run this all automated, robotic-like, and you can have them shoot these survey prisms on specified intervals. Now, the example here, it's a larger operation, but what we really want to focus on is just the graphs here of looking at as we were tracking change in distance, change in movement from a semi-baseline condition of not much going on to now we have kind of a wedge top line failures start to develop along some geologic contacts. But as things were going, we could pick up and quantify that, yep, not only are things moving, but things are really starting to accelerate. And then, you know, as you are both monitoring areas of movement and you have some of these installed and stable areas to compare to, you know, that's kind of what we see here is, okay, failure occurred, and then we were able to, you know, maintain some of the prism monitoring to show that, okay, you know, failed, you've kind of released that energy, and things have, you know, come to a new equilibrium. GPS monitoring. Just first off, I'll stay here, you know, be wary of the just your basic handheld ones, or even using some of our phones to try and get points, because we know there is a bit of error, particularly in elevation and on those. But you know, if we do have a, you know, a higher grade GPS survey monitoring equipment that you can use out there, then you can, you know, install your fixed points, you know, maybe they're pin set stakes, you know, install a post, you know, a fixed post at some point that you can then put your GPS antenna on, and whatever interval the case may be, you know, a couple times a year, quarterly, monthly, like it depends on the risk, what you have around you, you know, go survey that in, take that point, and then, you know, update it, see, you know, just track it, you know, whether it's a basic Excel spreadsheet or, you know, something a little more involved, access database, or it's some other software coding, commercial software that'll, you know, you can upload this data and print out or spit out your charts, your graphs, tables to show you, well, you know, what change has occurred, and again, at what rate. Drones. Mike showed you some great pictures of, you know, how you can use these to get the visual, kind of be able to get the pictures, images, video, see what's going on, and then you can compare those over time. Well, likewise now, through use of either, you know, LiDAR photogrammetry methods, depending on the type of drone, is, you know, some of you may be using these anyway to survey, update your surface topography, maybe check volumes, you know, either volumes of material remaining, volumes to be mined, and, yeah, using it for your mine planning purposes that way. Well, there's our tools software out there that, as you're doing this and maybe updating your surface triangulation or topography, is you can start comparing surfaces against each other. Now, you know, this isn't going to work in an area you're actively mining where, you know, every few days, whatever you're digging out, you're pushing that high wall or slope back. But, you know, maybe you have other areas, the pit, other infrastructure, you know, high walls that, you know, have been either reclaimed or sitting a few months, a couple of years before you get back in the area. Maybe you have some stockpiles that, if the condition doesn't change due to you dumping or moving material, you know, use that topo, use that surface, and start trying to compare between to see if, okay, has something changed? Is it settling, or, you know, worst case, is something pushing out? And the ground-based, you know, 3D LiDAR scanners are, you know, kind of very, very similar. You know, set them up in a sense like a total station, get them geo-referenced in, but in this case, instead of the drones picking an image, your viewpoints from above, you can set these up, kind of scan, look at your walls, look at your high walls, pit walls, and kind of get a sense of, in comparing those, of, well, okay, we have this baseline condition, we've come back a month, 2 months, things are fine, and, you know, you come back later and say, hey, we haven't been over there digging, but, you know, we've got this bulge, we've got this area that we can now identify has started to push out on us. And just here's some examples. These ones are, excuse me, from, yeah, LiDAR scans. Again, another larger pit, but you can see, you can develop heat maps showing that, okay, green is essentially there's been no change. Red, you get your extreme reds, and in this case, they're off the scale, but you start seeing blue is this where you've lost material, going through your yellows, oranges, reds where you've gained it. So you kind of see some of the upper parts of this slope that have the blue halo around it, but that means, well, you've lost material, and then you can start seeing benches here where it's filled in. Structural failure example, a large wedge on the right where the toe's already starting to push out. But again, you can use some of these tools to just kind of look at overall large scale, what's going on, what's the limits, where do we have concern of, sloughing, raveling, or material movement, and potentially what are those bounds, and again, just be able to quantify them. Hit on this one quick, INSAR, use of satellites. Becoming more and more widespread. Some items you just to watch for, be careful here, is just vegetation, and then what your satellite intervals are, what's your frame of reference, just really what's that angle versus what the potential angle is of movements. So it is beneficial, it is useful, but again, it's not going to help for a day-to-day active aspect of your operation, but potentially areas that are looking for reclamation or need to stand there a bit. Just talking clinometers quick, everything we've talked has been surface. Like I said, surface examples, see what's going on. Are you impacting your surroundings? These ones you would actually need a drill, but come in, create a boring, and install some inclinometer casing, which is special grooved casing where you can either manually or automated run an instrument up or down. Case being, if the slope's moving, the casing will move. So as you survey it with that instrument, it's going to tilt different if the slope's moving. Others, TDR, just kind of like looking for a time fault in a wire. You just run cable, grout a cable in a hole, and if it's moving, it's going to pinch or shear that cable. And just like you were looking at for a failure on an electrical line, you can at least try and find out what depth something's moving. Now, again, these are more involved. You need some form of drilling, but they are tools, like I said, if something's moving, something external to the operation is occurring. So now I'm just going to take us through, okay, what can we do with this now? So we've gotten our photos, gotten our images. We're in a case where we're able to quantitatively collect data, collect information. What do we do with it? There's basically it's finding what works for you and being consistent. If it's just a lot of photos, file organization, folder structure, years, dates, times. If you've got a larger operation, make sure photos are separated out. So if you need to go look at one, they're not all interspersed, intermingled. Or if you're collecting the data, is it equipment that came with the software that does it for you, or do you need to track or build the data in an Excel sheet, simplest case, and see what's going on? But where that leads to is just making sure we're not just taking photos for the sake of taking them. We're trying to then understand over the course of our operation, are there changing conditions? Is there something we need to be concerned about? Have our operators recognize that, hey, something's moving, and report them back to us. And well, what do we do? Well, how long ago has this condition been in place, or what's changed? Is it changing to where we think it's accelerating, or something's going to happen, something's going to occur, and what do we do about it? So the best practice that's last, I know, maybe decade plus now, as it's grown into the mining industry, is the use of a trigger action response plan. And in simplest sense, I would say to remind us all to, when we were in elementary and you regularly do fire drills, alarm goes off, everyone gets up and goes. Well, that's really what this TARP is. It's you guys as, maybe whether you're the owners, the managers, technical staff, maybe some operators of the operation, it's developing a plan in advance that, okay, we have this occur, this movement, this acceleration. What do we do? You get in those moments where, maybe something's occurring, get a little bit excited. Folks may get a little foggy on, well, what do we need to do? You can't think at the moment. Well, at least it's already laid out. You can pull the page, the table, the flow chart, the binder, whatever you have, pull it off the shelf, look through it, and you have this plan to where it's like, okay, well, what's our thresholds? What causes us to initiate this plan? Okay, and what are those procedures? Do we just block it off, barricade it? Is there any external folks we need to let know? And then how do we assess? Okay, how do we evaluate? Okay, what do we have? What's the risk? Is it getting worse? Is it changing? What do we do? And how long do we then keep the area closed? Until it's been either mitigated or we brought in, maybe other folks come in, take a look, and then after that's all said and done, there's got to be a specified plan for reentry. So it's not just, oh, it looks good, let's go. You know, it's making sure everyone is also on the same page and has a voice and ensuring that it's safe. So these can take on any measure, basically any scale. They can be triggered either by the geologic conditions we talked about, or maybe operational or environmental. You have a large storm coming through, rainfall, you know you've got an area of the pit that's sensitive to that. You know, that can be it too, if, oh, we expect, you know, X inches of rain in an hour, a day, whatever. That may be enough to then be your basis. You either monitor visually, keep track of what's going on. Those thresholds are exceeded, and then whether it's a table, a list, a bullet point, again, it's a, you know, there's no specification here. It's what fits your folks, your operation, is then determining, well, okay, this has occurred. What do we do? Let's finally just talk a bit on key guidance. You know, hopefully we've been able to share some things for you guys to, you know, at least think about, consider if you get in those situations. MSHA, they've got a lot of great training info on their website. NIOSH, they do as well. A lot of research looking into, you know, safety of miners and operations, as well as just some various industry-focused societies and associations. You know, put out a lot of great stuff. Or if you're in an area nearby, college, university may have done some research, done some studies, be able to provide you with some information. So with that, yes, thank you for listening to Mike and I's portion. I'm going to kick it over to Kyle, and he's going to lead us through any of the questions, answers that have come through. Kyle?
Yeah, thanks, Russ. And first, we also do want to share that both Mike and Russ will be at the upcoming International Slope Stability Symposium in Tucson. That's this October 17th through the 21st. If anyone else is attending, they'd be happy to catch up, chat a little bit, and answer any questions you've got. So it looks like we got a question here for Mike. Mike, how do we decide whether an assessment or an audit is something we need to do?
Sure. I'd say in my experiences, usually where this gets triggered is one, there's been some sort of a failure on a site, say in the overburden, the operations are concerned, so they call us to come out and take a look. Certainly another situation is if MSHA has been out and there's a K order. But the other one that's a little bit more on the proactive side is if you're entering into a new area of the mine, a new pit, maybe a greenfield area or something you haven't been in before any sort of a pit is done. A study to kind of come up with a basis for ground control plan is oftentimes done.
Awesome, thank you. Then we do have a few more slides to go through, but in the meantime, if there are any additional questions, please go ahead and use that Q&A feature at your top toolbar to get those in. Again, if there are any additional questions that pop up over the next couple of days or at any time, please reach out to Mike and Russ. Their emails are here. Anytime in a day, I think they're always willing to help and do what they can. And not able to advance forward, but again, a video presentation or a video recap of this will be sent out as well following this, so you'll have everything on record and the ability to contact us at any point. Do we have any other questions before we go?
It looks like there might be a couple here, Kyle.
There we go. They're coming now too.
Yeah. So I can target. There's one on here. How do you determine when you want to set a TARP action limit? So a lot of the instruments that Russ talked about where we kind of get in a specific quantifiable measurement. It's important to get a lot of those instruments up and develop a baseline. So you see kind of in general, there's always going to be a little bit of movement, but once you can establish that baseline, then you can start to look for deviations from that baseline that indicate something different or unexpected is about to happen. So I would say after a baseline is established, ideally, then you can start to set specific actions. And you know, for example, you know, if you use like a 1/2 inch or 1 inch of displacement, you want to be notified, you want to have a group notified. But that would be the approach to start to develop. Why do I want a certain number to be my action limit?
Yeah, I guess I'll agree to that too, is, you know, when we're talking ground control and slope monitoring, it is really identifying that change. And to play off of it, Mike's comparison of, you know, say you've got 6 inches a day of movement, but it's constant. Okay, yeah, that is a bit of movement. It is creepy. You do have something going. But I mean, it's a manageable condition, as long as you don't have any other factors around the site, or it's not, moving back to some infrastructure. But if it's staying constant, then you can manage it, you can watch it. Whereas if you have an area that's you've been monitoring and it's okay, we're going to set up, look at triggers, and it's been like no movement, and then all of a sudden it's like, well, 1/4 of an inch a day, 1/2 inch a day, and it's just kind of progressively changing. It's like, okay, yeah, that's a fraction compared to this constant 6 inches a day, but that's changing, that's accelerating. That's like, hey, we've got a condition that's changing over here. We need to respond. So yeah, it's really, you set those triggers based off of knowing what you have, and then does that condition change?
Awesome. And then another one coming for Greg, for Mike and Russ. Can you discuss certifications, relating to coal impoundments, dams, et cetera, and then whether BAR has individuals certified in that? We're talking a lot about high walls, but dams additionally.
Sure. So yes, I guess the short answer is yes. MSHA has particular requirements around impoundments, particularly on the coal side. But typically, approach we'll have on anything like that, we'll have an engineer record that's certified within the state where the operation is. But particularly with someone who's got experience with those sorts of, whether it's coal impoundment or a pond that requires like an earthen dam, usually that's EOR type certification.
And then this one's for Russ. Russ, what are some basic costs with the GPS monitoring system?
Oh, I still say, it may vary a bit depending on, do you have the base station equipment? Just to make sure you're calibrated back to that. I think probably 20,000, give or take. It's been a good realm of what I've seen. Again, depends on, what you may have or what you may be tying into, but kind of the really good survey, great stuff, you're probably around that 20, 25.
Yes, and we're going to open up for both. Looks like Albert, you got a question?
Yep, I have a question.
Go ahead. What you got?
I work for a mine in Ghana. Like, I'm a current MST student, but then where I worked as a mine surveyor, and then we used the total station and then the drone technology to kind of monitor the tailings facility and then the high walls of the mine. But then my question is, what do you really have to consider before selecting a technique to monitor a facility? Or because I think I missed a lot of the presentation. I had a class and I couldn't really join in on time. So I want to find out, what really do you have to consider to select a method for any monitoring activity, being in a high wall, being in a tailings dam, or whatever? What do you really have to consider before you can select that particular technique to use, being it the drone technology or the SSR or whatever? What do you really have to consider to decide on whatever technique you want to apply?
Sure. I can take an initial shot at that. So I think one is understanding of risk. So the particular area where you may be working, what's the elevated risk or the degree of risk. Secondly is understanding the geology and the ground conditions. I'll say ground conditions, not from the sense of stability, but what is there. And so, for example, if you have an embankment dam and you know that there's, say, a low strength clay material that's underneath that foundation, that's going to drive your decision to say, put an inclinometer in that extends through that weak zone, so you can look for movement in that area. If you have a hard rock mine with a very critical haul road, that might trigger consideration for more of a permanent radar type scanning system. So there's no one answer for all that, and cost is certainly a piece of that as well. But understanding the ground itself helps give you a basis for which techniques start to make the best sense.
Yeah, I'll add in too, because it is the gray. I'll say it is a gray area when it comes to slope monitoring, and I've been involved with other, you could say, groups, committees, organizations, or even when talking to the regulatory folks. They're asking about, well, what's the break point of? Your slope went from 40 feet to 100 feet. you know, you say in a quarry operation, obviously large scale mining, you know, bigger, you know, maybe it's, well, you went from 200 to 300. Okay, well then, you know, here's the check the box. So, well, that means you go from manual to automated prism to, oh, no, now you're 1,000. Well, that absolutely means a radar. I mean, it's really hard to say because, you know, everyone's site geologic conditions, you know, risk are different. I mean, maybe you do have a pit that, or quarry that, okay, it's a couple 100 feet high, but it's an inactive area where no one's been in for a few years. There isn't a risk. You don't have anybody around you that it's like, okay, we can still use a manual method over here to monitor. Whereas maybe at the other side of the pit, it is, you know, 75 feet high, but it's active, you know, there's some faults, there's some contact, you have some people there every day to where it's like, oh, well, you know, maybe we need to go automated in some form or another. So yeah, I understand your question. It's one I had struggled with working on an operation because it's not a hard set. You know, yeah, you've got this situation, go and deploy this. You really, like Mike said, you've got to bring in all those site factors, the geologic conditions, your, you know, impoundments. Well, how was it constructed? Is there any concern with how it was constructed? And, you know, what's downstream? Yeah, short answer is you've got to think of everything.
Oh, that's great. All right, thank you so much, Mike and Russ. And I think I have a paper that I actually wrote a paper on the various techniques that we use to monitor all these mine facilities. So I'll shoot an email to you guys, and then I have some other further questions that I would want to ask more, but I'll send an email to Russ or Mike. Thanks so much, guys.
Sounds good. Thank you.
All right, looks like we're getting close on time. Mike and Russ, you guys feel like taking one more?
Sure.
Sure.
Okay.
If there's,
right.
Yeah.
So this one is, can one of you discuss using hydrological monitoring, you know, that's water levels to assess high wall stability and whether BAR has done so?
Sure. Oh, go ahead, Russ.
I was going to say, I speak to BAR has directly or indirectly, we'll say prior to, we used it, and I worked with my hydros to, you know, it is very much make sure they communicate. They're watching, you know, talking to me about it. They're starting to see, you know, if there is any, say, unexpected, you know, we haven't turned on a pumping well or added some more drains to, you know, where that may cause something to either drop or, you know, a storm event, changing condition where it's infiltrating. But, you know, their monitoring is all subsurface. So if my geotech, you know, we're only looking at surface movement of the pit, you know, maybe their piezo's are picking up a, you know, either spike, increase in pore pressure, or an immediately start drop. That may be a sign that, hey, something had to have shifted, you know, internally or within the rock mass, within the soil mass, to where it's like, hey, that maybe we need to go look over there, you know, tie that back to the geotech. I'd say the other easy one is, you know, the piezo wires can sometimes act as TDRs too, of, you know, if you're monitoring and then all of a sudden, like everything in the boring, you lose it all, you know, maybe that's a sign you had a contact that shifted or sheared, and loss of the hydro monitoring tells you that, hey, we actually do have a ground movement.
Awesome. Well, thank you, Mike. Thank you, Russ. That wraps us up on time. So big thank you to you guys, and even bigger thank you to all those who attended with us today. Again, we'll be sending out a video recap of this presentation, and again, contact BAR with any questions you may have going forward. We look forward to working with you and seeing you at our next webinar. Thank you.